Okay, so today our agenda is to find out how to write an HDL code to control the speed and direction of DC and stepper motor. So before we get started, let us have some introduction, and we will see as to how we will implement this DC motor using Verilog code. Okay, and we will be implementing this using Spartan 6 FPGA kit, and the equipments required will be the software which you all are aware of, Xilinx 12.1, and we'll be using a JTAG, FPGA kit, etc. Okay, so before we get started, let me just give you an introduction, okay, as to what is a DC motor. So we'll start off with DC motor first, and then we will get into stepper motor. Right, so in DC motor there are two wire connections, okay, and basically what we are trying to do here is we are trying to control the speed, and we are trying to have a control on direction of two types of motors. One is DC motor and the other one is stepper motor. Now the difference between these two motors are that, DC motor has a continuous movement. It could be either in clockwise or anti-clockwise. Stepper motor also moves in clockwise and anti-clockwise, but the only thing is that stepper motor moves in terms of steps, but DC motor has a continuous movement. Okay, so we will be seeing accordingly. We will interface the kits and we will see how these two are separate or how these two are differentiated. Okay, now how do we do this? How can we control the speed? We are using something called PWM, which is pulse width modulation. So if I increase the pulse, then I'm going to give more potential, so which means the speed of the motor will increase. If my pulse width is less, then the speed of the motor is reduced. Okay, so this is how I can control my RPM. RPM is the speed that I just spoke about. Okay, so most of the DC motors, they are calculated in terms of RPMs or any rotatory movement. Okay, it can be your vehicles or it can be DC motors or any sort of motors. We take them in RPMs, which is nothing but revolutions per minute. Okay, some best examples can be your fans, okay, and the fans which are used in your computers or laptops, which is used for cooling the processors. Okay, all these things. Right, so this is your introduction for DC motor, and before we actually get into the code, okay, the coding section, we will look into the theory, okay, and we will see exactly as to what it means, and then we will see step by step as to how the program is getting executed. Okay, so you all should understand that for the inputs we are taking row, clock, direction, reset. So all these are going to be my inputs, and towards my output I'm going to have two types of directions, which means the rotatory movements of my DC motor. So it's going to be clockwise direction and it's going to be anti-clockwise direction. So for this I am naming it as MTR1, motor 1 and motor 2. Now to do this we need some control signals, isn't it? So these control signals are nothing but your DIV. Okay, so this is taken as a 26-bit vector. I will show you in the code as to how we are representing this, and then we are using clock D and we are using tick. Then we need to use a counter which is 8-bit, which will be 7 down to 0. Okay, and the duty cycle. So duty cycle here, the range is from 0 to 255. I can pick up any numbers for that matter, and I can assign. Okay, so what am I doing with this? I can actually increase the width of the pulse. So once the pulse width is increased, the speed of the motor increases. Once the width of the pulse is reduced, then the speed of the motor is reduced. So ultimately I'm having a control on speed of the motor using my duty cycle. Then rho freeze to 0. This is nothing but it's representing the 4 push buttons. I'll be showing you exactly as to what are these push buttons in the kit. So these push buttons are for the speed. So I will be assigning these duty cycle to the push buttons. Okay, fine. So now let's get started with the code. I will explain the code as to how it functions. So we have always at positive edge of the clock. Okay, so which means the positive edge of the clock is taken as sensitivity list. Okay, so you can recall the concepts of rising edge and falling edge. So here when I say pause edge, it means the rising edge of the clock is taken into consideration, right? Then you have something called assign clock D is equal to div 8. Now this is something where what we do is our clock frequency is too high. The clock frequency that we use for our kits, okay, is too high. So what we do is we try to divide this clock frequency, and the 8th bit of div, okay, that's what it says here. Whenever it's in the square bracket, it means which particular bit, and the number is representing the number of the bit. Okay, so 8th bit of div is used as clock to the program, right? So next we have assign tick is equal to row 0 and row 1, row 2, row 3. Okay, now this is performing your ANDing operation. Okay, so which means the buttons, when it is not pressed, okay, when it is in relaxed mode, it means that it is representing state 1. Whenever the button is pressed, okay, then it becomes state 0. So how do we do it? So first we need to assign, or we need to enable it. So we use the command assign enable 1 tick binary 1. So which means B is your binary here, and the value given is 1. So once I activate my enable, then my next work is actually to work on the clock. So the positive edge of the clock, now clock D, as I told you, this divisions, okay, this divisions you can see here previously we have used. This divisions is equated to clock D. So whatever value is here, that is actually across your clock D. So this clock D, it becomes your sensitivity list, and at every positive edge, which means rising edge of the clock, your clock D is tracked, and this becomes a continuous loop. Okay, it becomes a continuous loop, and the counter is incremented whenever it has a positive edge of the clock. And next we come down to something called neg edge tick. Now this is where exactly the buttons comes into picture, the push buttons. So we have about 4 push buttons, and whenever the key is pressed, then it becomes 0. Whenever the key is not pressed, then it is in state 1. So for this, what we do is we use case statements, and we take row as the sensitivity list. Okay, case with respect to row, and this is representing 4 tick binary format. Okay, now this represents, each bit represents push button 1110. So 0 means whenever the first key is pressed, then you have 0 here, the second key is pressed, the third key is pressed, the fourth key is pressed. Now the duty cycle, okay, is given as 250. As I told you previously, this is an integer, right, which ranges from 0 to 255. The duty cycle range is from 0 to 255. So I am going to assign particular values, okay, as follows. So I will give 250, 190, 100, 40. So based on the keys pressed, okay, the value, the integer value is assigned to duty cycle. So why am I doing this? So that I can actually vary my pulse width. So that's my motive. And we need to always take a default case. If we don't take a default case, then we have learned that it gets into an confused state. So which means in order to track this particular information, it has to have an extra hardware. It could be a flip-flop, okay, or it can be a latch. So in order to reduce all those complexity, we use default. So this was about the speed. So next, now we will see how we are going to control the direction. Either I'm going to move it in clockwise, or am I going to take it into anti-clockwise direction. So for this, I'm going to use reset and direction. So these two becomes my sensitivity list. Okay. So whenever reset is 0, what I'm doing here is I'm assigning 0 values to both of my motors. So when I assign 0 value, it means that both of the motors are non-functional, which means it is not functioning. Next, I've used an else. So if reset is 0, else if reset is 1. If reset is 1, and I have another sub case, which is if direction is equal to 0. So when I take direction is equal to 0, the motor should rotate in the clockwise direction. So how do I assign it? By giving motor 2 is equal to 0. Okay. Now these are all statements where you should try to understand where 0 is given to motor 2. Okay. Just like your blocking and non-blocking concepts that we have seen, right? So this is your non-blocking assignment. Okay. So motor 2 is given 0, and then whatever speed that we have assigned to duty cycle, that is being given to counter, right? And motor 1 is enabled. So which means 1 value is given to motor 1. So what happens because of this? It is telling my direction is going to be 0. Okay. So which means the motor rotates in clockwise direction. Okay. Now we will see the other case where I will have direction is not equal to 0. Okay. So in that case, I reverse the values. So motor 1 was given 1 and motor 2 was given 0. So here I reverse the case. Okay. So the direction, when it is 1, then the motor rotates in anti-clockwise direction. And we can see that the speed is assigned based on the duty cycle. The values are given to counter. Okay. So this is how your motor actually functions. So we have seen how the speed is taken into consideration with respect to duty cycle, and also now we have seen as to how we are controlling the direction, the clockwise or the anti-clockwise. So we will see the summary here as to what all we had studied so far. So when reset is 0, direction and rotation is nil. When reset is 1 and direction is 0, it goes into clockwise, and then when direction is 1, it is anti-clockwise, right? So this is with regards to your code. Now what we will do is we will try to get into the software, okay, and we will see as to how, or we will see the execution steps. So once you click on Xilinx 12.1, you should be able to see this window, and here you can click on File, New Project. You'll find this New Project wizard, and here you can type in your name of the program, After this, you can choose the appropriate work location where your programs are going to be saved. I have saved it, I've created a folder on my desktop, so I'm going to select that folder, and you should be able to see the link coming up here, right? Then you can click on next. So these are some of the settings that needs to be done in this wizard. Your family should be Spartan 6, device should be XC6 SLX9, then your package should be TQG144. Simulator, you should be choosing your iSim, right? Then your language is going to be Verilog. So after this, you can click on next, and then now click on finish. So once you click on finish, you should be able to see this window. Now here you have an icon, new. You can click on it, highlight text file, click on OK, and you should be able to see this blank page. Now this is where we are going to type our code. Okay, I have the code here with me, so I'll be just putting it. So this is your full code, and we have to save this. So click on save. You should be able to see a new window popping up, and here you can type in the name of the program. So once you're done with that, you can click on save. Before that, just verify if it's Verilog. The option save type should be Verilog. Then click on save. As soon as we do this, you should be able to see your keywords. Keywords will all turn blue. Okay, and that is another confirmation, okay, where you have saved your program. Next, you can right click and add source. Then add source window comes up. So here you have to select the file that we just created and then click open. So once you do that, you should be able to see this tick mark, which is telling you that the program is added, and then you can click on OK. So once we do that, this type of window appears. Now you can click on simulation. You can select the .v file, left click once, then click on the plus symbol here, iSim simulator, and you can double click on behavioral check syntax. So this is going to check your program if it's proper. So you should be able to see a green tick. So this indicates that the process syntax check is proper and there's no error in your code, right? So now you can right click on this, click on new source. A new window comes up. Okay, so this window is called new source wizard, and you need to select the third option, which is implementation constraints file. Now remember, I was telling you regarding the UCF, user constraint file. So that's what we are going to do here. We are going to create the UCF. So So once you select implementation constraints file, you can give the file name. Okay, you can probably name it a little different, DC motor score interfacing, and since I want to differentiate, I will probably put it as UCF, which is nothing but your user constraint file. So once we have this, make sure there's a check on add to project, and then you can click on next. So it gives you a confirmation summary window telling you the association of your program. Okay, you can click on finish. You'll be able to see a blank window now. So in this window you will have to type your UCF, right? So we will put in the UCF file, user constraint file. So I will explain to you in a bit as to what this user constraint file is. Now, as you all know, we are using FPGA, and we are also using FRCs, okay, your cables. So this needs to communicate with your FPGA, and it is associated with a particular number, pin number. So P represents to pin. So pin 55, clock is assigned to pin 55, and similarly you can see your enable is associated to pin 5, then your motor 1 is associated to pin 6, pin 38, then row 0, 1, 2, 3 is associated to 57, 59, 62, 67. Then the direction control is with pin 81. Okay, then with regards to your reset, it's with pin 80. So this is your UCF file, and you can click on save and click on implementation button. Now once you click on implementation button, we'll have to click on synthesize XST. Now remember, your kit should be connected. Okay, so that is when we will get the check marks with regards to synthesize XST. I will show you in a while as to how this is done. We will interface with the kit, and I will show you how synthesize is done. So once you double click on this, it should actually work out with your RTL schematic and your tech schematic, in short for technology schematic. It should be even able to check your syntax, and it should be, next process will be clicking on generate post synthesis simulation. So after check syntax, it will actually generate post synthesis simulation. So all this happens when you double click on your synthesize XST. So we should be having the kit connected. After that, we will be clicking on implement design. Implement design will again have translate, map, placement and routing. Now, as we have discussed, these are nothing but translating the information, whatever code that we have written. So those information is translated, it is mapped, and placement and routing, just like how we have studied in our theory classes. So the same process happens here. Placement and routing is one such important parameter where we place components. We try and place those components which are very closely, having a lot of connections. We try to place them very close, and those components which do not have more intermediate connections or connections between them, we can place them afar. So this is what happens in placement and routing, and this is a repetitive process, so which means it keeps going on and on till it comes to an optimum design. So I'll be showing you in the upcoming sections as to how we implement design. So we are translating the information from our code into the hardware. So what kind of hardware we are using? We are using your HDL Spartan kits, the Xilinx Spartan kits. We are using the 6th version of Spartan kits, so that's why it's called Spartan 6. There were previous versions as well, so this version is better comparatively when you see your older versions. And with this code we'll be able to communicate with your FPGA, just like how I have shown you these pins. Your user constraint file has pins, so these code will actually get connected to those pins, and accordingly it starts getting executed. So which means what we are trying to do here is we are trying to send the information from our program, and we are going to have few interfacing kits, okay, and to those kits we are sending information from the computer. So which means your computer should have a USB connection where you transfer information through USB cable to a USB programmer. So USB programmer stays in between your computer and your FPGA kit. Then your FPGA kit, once it gets the information, once the Spartan kit gets the information, then we have to send that information to a particular module. For example, in this we are using a DC motor, so which means we have to connect it to a DC motor. If suppose we are doing a stepper motor, I'll be showing after this as to how a stepper motor is connected and what connections are involved. So we'll be using a stepper motor module there. So similarly, we should be able to connect along with the Spartan kit, and it should be able to communicate with your other modules. So all this happens only when we properly specify as to which pin is allocated and what functionality is being done accordingly. If not, say for example, instead of pin 55, say I use some other pin, then there is no information that's getting passed, so which means there is loss of information. And these are all standard, okay, these are all company specific. You get this information from the company and we follow accordingly the specific pins, just like how you have your normal ICs which will have ground at one particular pin number, then your VDD at one particular pin number. So the same process is what we are following here, right? So every pin is associated with its own functionality, and we will stick to it. So now you will be seeing as to how we will implement design, then the translation happens, and the mapping happens, and then placement and routing happens. So we will go ahead and see as to how exactly these things are done, and how once connected, how these actually coordinate together and get things worked out. Okay, so we have to select the file here, and once the file is selected, at the bottom you should be able to see the options, okay, where you can click on synthesize XST. So once you double click on that, you get a dialog box. Click on yes, okay. Then after that you can click on implement a design. You should be able to see 3 tick marks against translate, map, place and route. The next process is to click on generate programming file. So this connects to your hardware. This creates the bit files needed corresponding to your hardware. Okay, so you should be able to see that tick mark there. Okay, so now we will see these pin assignments. Okay, so as per pin assignments in your UCF, okay, your FRCs are connected accordingly, and then we will see exactly how we connect them. Okay, so these are your FRCs, the charts, right, showing information with respect to pins, the FRC ports, FRC 1, 2, 3, and it goes on. Okay, and yes, so now we will see how exactly it is connected. So one end is connected to the socket, the power supply, and this is the power adapter. So once you connect this to the power supply, you should be able to see the light once you turn on the switch. Okay, once you turn on the switch, and the other end of the cable is connected to the FPGA kit. So that's the way it's connected. And once we turn on the switch, you should be able to see all the LED lights glow. So this indicates that your board is functional and all the circuitry is fine. It's ready for operation. It's ready for accepting inputs. And the USB programmer that you see, okay, is actually in between your computer and your FPGA kit. So whatever program that we write gets dumped through the USB programmer. Okay, so it translates the information to FPGA. So once connected, even with this USB programmer, you should be able to see the light glow. Okay, so that's how it looks. Okay, and these are, as I was mentioning, your FRC information with regards to pin numbers, and these are the ports. Okay, FRC1 in your Spartan kit is connected to your DIP switch pins in the DAC board. Okay, those are your DIP switches. Then FRC7 is connected to keys. Okay, FRC7 from your board is connected to the port, okay, called keys. This is actually your GPIO, general purpose input output. Okay, and your FRC9 from your board is connected to the DC module, DC motor module. Okay, so you should be able to see program succeeded, after which this becomes fully functional. Okay, so that is the information that you should be able to see. Program succeeded. Okay, so when you turn on the switch, the motor should the DC motor should turn on, and you can off it as well with the same switch. Okay, and the second switch is for the clockwise and anti-clockwise direction, right? And you see the push buttons at the bottom, the 4 black push buttons. So these are for your speed control, as we had discussed in the program, the speed control of your motor. Okay, so this is how your DC motor functions. We have written the code, we have dumped it, okay, into the kit, and once we have the confirmation on the software, as I showed you, as we have program succeeded. Okay, so this is the code for your Verilog code, okay, Verilog module for the speed control and direction of your stepper motor. So the procedure remains the same, just like how we discussed for DC motor. Okay, so we will go ahead and try and understand the concept involved with the stepper motor. So this is your block diagram where you have towards the input as clock, reset, direction, row, and towards the output you have D out. So D out is of 4 bits. There are few more other signals that are involved here, which is div clock, okay, clock division, which is your 26-bit vector, just like how we saw in the DC motor. Okay, and we have a register which is of 4-bit. Now we will go ahead with the code explanation. So the first section is going to be speed control, okay, and then we will see how the direction is managed. Okay, so always at positive edge, so which means your rising edge of the clock is considered. Okay, and there's an increment done to the divisions of clock, okay, which is div clock plus 1. Then after that what we do is we take row and div clock as sensitivity list. Then we use cases, okay, we use case statements here with respect to row. Okay, so what we do here, just like we saw in DC motor, okay, so here we'll be using 00, 01, 10, 11, okay, and accordingly the speeds are assigned based on the clock division, okay, the frequency divided, and this in turn will control the speed of the motor. So you can see here 21, 19, 17, 15, then by default I am giving back to 21. Okay, so as I mentioned in the previous sections, that if in case we don't give this default case, then we need to have an extra hardware. It can be either a flip-flop or it can be a latch to maintain the value. So in order to get this confusion cleared within the programming structure, we use default. So case had started here, so we will end case and we will end this particular section. Next we will see how the direction is controlled. Okay, so you have always at positive edge. Okay, so you have 2 parameters here. Okay, your initialization of clock and then your direction. Okay, that is your int clock and direction. So if reset is equal to 0, okay, if reset is equal to 0, let me give a random value. Okay, let me give a 4-bit of binary form and the value is 1001. I give this value to register. Okay, now if direction is equal to 0, so then I will experience the clockwise rotation. Okay, clockwise rotation of the motor. Now as you all know, okay, we are discussing about the stepper motor. So in the stepper motor, unlike your DC motor, as I mentioned previously, it moves stepwise. So it can be either in clockwise or it can be in anti-clockwise, but it doesn't have a free movement compared to your DC motor. So that's the difference. Then here you have register is equal to register of 0-bit, comma, register 3:1. So what is going to happen when we see this flower brackets is that concatenation operation happens. Okay, and if direction is equal to 1, this is for direction equal to 0. If direction is equal to 1, then I'm going to use this format of concatenation. So which means when direction is 0, I'm going to use clockwise. When direction is 1, I'm going to use anti-clockwise direction. Now how does this function, how does this concatenation operation happen? So we will see it here. So basically since we had taken 1001, okay, so your registers are broken up into the 3rd bit, 2nd bit, 1st bit and the 0th bit. So accordingly the values are stored 1, 0, 0, 1. Now I have used this command line, right? So register is equal to register 0, comma, register 3:1. So here first the value which is in 0-bit, that is taken. Okay, so if you can see here, the value of 0-bit is taken and then the values of 3 to 1 are taken. So an appending operation is happening, so this is in turn called your concatenation. So if you compare the values with your data 1001 and your final value 1100, you can see that there's a shift that is happening. There's a circular right shift that has happened. Okay, now we'll go with the next case. Okay, the next case is for this else, right? So we saw register 2:0 comma register 3. So in this case, how is it going to work? So it's going to be the reverse case. So here register 3210, as usual I'm going to have 1001, and the command that I'm going to give, or the instruction that I'm going to give, is register 2:0 comma register 3. So here also we will have concatenation operation. Okay, but just that the values of 210 are taken first and then the value of register 3. So 210 and then 3. So if we compute the value, it becomes 0011. So when you compare the values which was given and the final value in the register, we can see that a circular shift has happened, but this time towards the left. Okay, so this is how your stepper motor actually functions. Now that we have seen the functionality of your code, okay, the procedure for execution remains the same, just like how I showed for DC motor. We will go into file, new project, and putting in the main code, and once we have the main code, then we go with behavioral check syntax. Then once that is done, then we go with the UCF file. Okay, so once we have the UCF file, we will save it. Once we save it, then we will go into synthesis, then we will go into the other mapping, placement and routing, all these options. Then we will click on generate file bit. Okay, so we will discuss about it. I will show you the video as to how exactly it functions. Okay, so I think you would have understood the concept of stepper motor program, right, as to how it's functioning. And right now, we will see as to how the programming is done. Okay, so as usual, as I mentioned previously, we will be going into file and new project. Okay, then you can type in the name of the program. You can select the target folder. Okay, name the folder so that it will be easy for you to find out, and take the files from there for further reference. So once you have named, you can click on OK, and then you can name the file there as to what you want your file name to be. So once that is done, you can click on next. Okay, stepper motor, then we'll click on next. So once this is done, just verify your configurations here, the settings. Okay, as I told you, it should be 6SLX9. okay, the family Spartan 6, then click on finish, say yes. Then this is the kind of screen that you would see. Click on new, then text file, okay, then you can type the program. I have it here, so I'll be putting it in there. Okay, so I'll be taking the complete program and I'll paste it there, right? And then next thing is for us to save it. Look for the appropriate type and file name. So file name, we're going to name it as, we'll name it as stepper 1. Click on OK. You should be able to see the color change in your text, right? Then right click, add source, select, click on open. You should get the confirmation and click on OK. Fine. So that's your program there now. And now we can actually go ahead and check for the behavioral syntax. Select the file, come at the bottom, and at the bottom click on the plus symbol, then double click on behavioral check syntax. So you should be able to see a green tick there referring that it's correct. Then right click, new source. So this is where we are going to add the UCF file, and put the name of the file. UCF, remember, is your user constraint file corresponding to pin numbers and the FRC. So it maps between them, pin numbers of your FPGA. So after naming, click on next and then finish. So this is where you're going to type your UCF or your constraint file. So I actually have it, so I will open it. I'll take it, then I'll put it up there. Silence the UCF window. Yes, I'll be pasting it there, and now I can save it. Click on save. Okay. So the next one is I will get into implementation and then synthesize XST. Okay, this is a repetition. This is for your understanding. After synthesize XST, you can actually click on implement design. Okay, so translate, map, placement, routing. You should be able to see 3 tick marks there, and after that you'll be clicking on generate programming file. So there you go. Click on write programming file, and you should be able to see another option there. These are your FRC information. As we have seen, the programmer, USB programmer, will be using FRC 1 to the DIP switch, the DIP switch. Okay, here we'll be using the first 4 switches. Okay, the first one to turn on, off, and then the speed. Then FRC 9 is actually used to connect to the stepper motor module. Okay, so once this is done, this is how your setup looks. Fine. So you can double click on the target device. You will get a new window. Okay, click OK, and then right click here, and once you right click here to this box, you can click no, and then towards the LHS click on the FPGA option. The new window, press OK, and you should be able to see that the identify is succeeded. Okay, then right click on Xilinx icon, select assign new configuration, then go to your file and search for the bit file, then click on no to the new box that appears. So you should be able to see that bit file there, and right click again on and click on program, select apply and OK. So you should be able to see program succeeded. Right now we will see the first switch is used for turning on and turning off the motor. Okay, so you can see it, you can take a close look at it as to how the stepper motor is rotating. And when I go with the off state, your motor stops rotating. Okay, then the second switch actually corresponds to the clockwise or anti-clockwise direction. Okay, so accordingly you can see the changes happening, right? Then the third switch and fourth switch correspond